Hello, my name is Jared Skeens and welcome to the Zoom room. Today we'd like to look at mechanics, work, energy, and power, part 2, the energy method. So in part 1, we looked at work and power, and we saw that work is in the form of joules, and we added that layer to what we've learned in the mechanics. Now this is actually the end of the mechanics our mechanics book here, and we want to look at specifically how this concept of work with joules can be connected with energy. It gives us just an added extra way that we can do some solving. So first off, we have KE, which is kinetic energy, and kinetic energy is basically energy in motion. So it has to do with your velocity. So to figure out kinetic energy, you'll take 1/2 of the mass times the difference of your final velocity minus your initial velocity. You can also write it like this if you want to distribute it and have 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. So kinetic energy has to do with energy in motion, and it's the difference between the squares of your final and initial velocities times the 1/2 mass. And that units of that will be joules, which if you notice was the same as work. The other type of energy that we have is potential energy. And potential energy has to do with your height above the ground. And so as long as you are above the ground, there is a potential for motion because this object can fall off the edge and travel downward, in which case it will change its potential energy into kinetic energy. Once it hits the ground, there's no potential for moving anymore. So for potential energy, it's mass times gravity. Remember, we use 10 for the mechanics book for Cambridge, and times the height, that is how far above the ground you are. You can also use height in the sense of the change in height. So if you are going from one height above the ground to another height above the ground, then your height would be that change in the height that you have. So this will give you your potential energy. And again, potential energy can be converted into kinetic energy. So actually, there's another little formula in here that you need to consider, and that is if there is no resistance, then your kinetic energy will equal your potential energy, or vice versa. It doesn't really matter which way you write it. So if this object falls off the edge and we don't take into consideration wind resistance or anything like that, then the entire potential energy will be converted into mechanical energy or kinetic energy. So if there is no resistance, then you can set them equal to each other. However, if there is a resistance of some form or another that you have to consider, then you're going to want to consider this, the total energy equation here, where remember joules in energy is also the same unit in work. So we can take the total energy found from work, that is the work from our driving force, minus the work done against resistance. That would be the total energy from a work point of view, will be equal to the kinetic energy plus the potential energy, or in other words, the total energy from the energy point of view. So you can set those equal to each other. Now let's just take a moment to look at the signs. On the left, this sign will always be negative. Why? Well, because your driving force is what is pushing you along, and this work just means it's multiplied by distance. So your driving force is the work done of your driving force over distance in one direction, and your resistance is obviously working against you. So this is always going to be negative because it's working against the direction of the driving force. On this side, however, this just means we add them together. It doesn't necessarily mean this is a plus, a positive sign. What you need to do for both of these is because the signs of both of them can be either positive or negative. When you're working with kinetic energy and potential energy, you want to think of it as in, are you gaining or losing energy? Okay, gain or loss. Of course, if it's gain, you're going to make it positive. If it's loss, you're going to make it negative. You're going to add those two values together. So either one of these will be positive, the other one will be negative. So in the case of kinetic energy, if you are going downhill, most likely you are increasing your speed, and that means your final velocity will be greater than your initial velocity, and so you're going to have a gain of kinetic energy, and so you'll put it in as a positive value. However, if you happen to be going uphill and your speed slows down, then your final velocity will be less than your initial velocity, and you'll end up with a loss of kinetic energy, and it will show up as a negative value. Same thing with kinetic energy. If your end height from your beginning height is higher, then you'll have gained potential energy, and you'll enter it as a positive number. However, if you have lost height from your starting point to your final point, then you'll have a loss in potential energy, and you'll enter that as a negative number. So for the gravity, you can just put it as a positive 10. You don't really need to think of the gravity as positive or negative. Just plug it in as a 10. You want to think of it as gaining height or losing height, and having that gain or loss determine whether you enter as a positive value or a negative value. Okay, so even though it says add, you are adding them, but one of the values will be positive and one negative. Again, if there's no resistance at all, then the two values are equal to each other. Okay, so there's a complete conversion of energy. Nothing is lost in the system. So this is what we're looking at for our new information. Now we want to add that into our cumulative collective knowledge that we have gained as we have went through and now are at the end of our mechanics textbook. So let's look at a few of the questions here. Okay, let's look at our first question and read it together. It says the total mass of a cyclist in her bicycle is 75 kilograms. The cyclist ascends a straight hill of length 0.7 kilometers, inclined at 1.5 degrees to the horizontal. Her speed at the bottom of the hill is 10 meters per second, and at the top it is 5 meters per second. There is a resistance to motion, and the work done against this resistance as the cyclist ascends the hill is 2,000 joules. The cyclist exerts a constant force of magnitude F newtons in the direction of motion. Find F. Okay, let's go back to our board and look at the information here. So we have the cyclist and the cycle is 75 kilograms. I just drew a bicycle as an object here. The cyclist is got a velocity of 10 meters per second at the bottom of the hill and 5 meters per second at the top of the hill. The distance or length between those velocities is 0.7 kilometers. Notice right away I have converted it to 700 meters because our units deal with meters, not kilometers. So make sure you're careful with that, 700 meters. The cyclist is exerting a force, sometimes we call it our driving force, in the direction of motion. And notice there is a work done against resistance. Normally I just put the number here, but because it's work and not newtons, I wanted to kind of point that out. So this is work done against resistance of 2,000 joules. Now actually, especially as you get through all these layers of the mechanics book, there you will find places where you can use more than one way to solve the problem. And this is true here. You could do this the way that we've learned before, where you would take Newton's second law, mass times acceleration, and set it equal to the net force, which is your driving force minus your force of resistance minus also the mass resolved parallel to our hill that we have here. You could do it that way. However, there's a few things that you would need to do. First, you would have to solve for acceleration. And you could use the Suva equation, v squared equals u squared plus 2as, because you have the distance, you have the velocities, and you can solve for the acceleration. You would also have to change the work done against resistance into force. So you'd have to divide this by the 700 in order to get it into a force. And you would also have to resolve the weight of this object horizontal or parallel to our inclined plane. So there's a lot of different things that you would have to do, and that is a viable method that you can do. However, in this particular video, we're looking at the energy method. So I'm going to show you a different way that we can solve the same problem, and that's using energy. So what we want to do is we want to focus on our two types of energy, kinetic energy and potential energy. So we'll start with our kinetic energy. So our kinetic energy, and by the way, since we are going uphill and you can see that the velocity is decreasing, this is going to be a loss of kinetic energy. So our loss of kinetic energy is going to be, and let me just stop for a second. Now, I told you there's two ways of solving this, and you might ask yourself the question, how do you know which way you should proceed with when you get to these questions? And you can solve them two different ways. However, there is a clue that you might want to use the energy method as opposed to Suvat and your second, Newton's second law. And that is because of the joules. Because your work is done, because the resistance is in terms of work and you have joules, that's one clue that you can use energy because you're already working with joules. Another thing that you have that helps is you have the two velocities, which is important for kinetic energy. You can use the two velocities in Suvat as well, but you have both of those available. And with potential energy, you need to be able to find the height. And because you have the angle and the hypotenuse, we can use our trig functions to find the height. So those are things that you want to look for. If we did not have this distance here, and if this were not in joules, then probably would have leaned towards the Suva and second Newton's law way of solving this. But because we have joules and this distance here, then we can use the energy way. Okay, so that's something to train your thinking by so that you don't get confused and frozen trying to decide which way to go. Those little clues like that can help you make a quick decision and then just follow through with it. So here we have kinetic energy, 1/2. Our mass is 75, and our final velocity is 5 squared. Don't forget to square it. It's the square of the velocities minus the initial velocity is 10. So when we run that through our calculator, we end up with a negative, because obviously this is going to be negative here, 2,812.5 joules. And it's negative because we are losing our kinetic energy. Now let's focus on potential energy. And so notice we started at ground level and we have increased our height. So that's going to be a gain in potential energy. So put gain in our potential energy. And this is mass, 75, times gravity. We'll just put in 10. We already see it's going to be a positive value here because it's a gain. And we need the height. So to find the height, we'll just drop our height down, make it a Sekolah, right triangle. So here we have opposite. So sine of our 1.5 degrees will equal opposite over the hypotenuse, hypotenuse being 700 meters. So our height is 700 sine of 1.5 degrees. So we'll just put that right here for the height. And our potential energy, when we calculate that, comes out to 13,742.9 joules, and it's positive because we gained elevation on that. So here we have our two energy. Now, because there is a resistance, we cannot set these equal to each other. And actually, we don't want to set them equal to each other because our variable that we're solving for is actually finding a force. So, but these are important for the total energy equation that we need to use because there is resistance. So now we can just set up our total energy equation. And our total energy equation is the work done by the force, or work done, I can call it the driving force. Work done by the driving force, which we don't know yet, minus the work done against resistance, which is 2,000. Okay, so the driving force is going one way and work done by it. And then we have the 2,000 going this way, and that is equal to our PE plus KE. So since this one is positive, I'll write it first, minus the 2,812.5. And so when we work that out, we get our work done by the driving force comes out to 930.4. Now remember, this is work done by the driving force. We want to find the force itself. And work is force times distance. So the distance is 700. So this is 700 F. The force times 700 is the work. So when we divide both sides by 700, the force of our, I'll put our driving force here. Our driving force then comes out to 18.5 newtons. 18.5 newtons is our driving force for this cyclist. Okay, so we did our kinetic energy, it was a loss. We did our potential energy, it was a gain. Because there's resistance, we use the total energy where we compare work with the work in joules with energy in joules. So work minus resistance equals the potential energy plus the kinetic energy and then solve for the force from that. Okay, so that's our first one. Let's look at the second one. Okay, let's read our second question together. Here we go. A lorry of mass 25,000 kilograms travels along a straight horizontal road. There is a constant force of 3,000 newtons resisting the motion. Find the power required to maintain a constant speed of 30 meters per second. Well, there's not a lot of information here, but let's again draw our diagram. Here we have our lorry. Remember, a lorry is the same thing as like a semi-tractor trailer, big truck. And it is going along a horizontal road. It weighs has mass of 25,000 kilograms and has a resistance of 3,000 newtons. And of course, the driving force, we don't know, it's moving forward. And it wants us to find power, which is actually what we covered in part 1. So a little bit of review here before we get to part 2. Find the power when it has to maintain a constant velocity. So constant velocity means that our acceleration is 0. There's no acceleration, and no acceleration means that our forces are balanced. There's not a net force, or the net force is 0. So that means the forces are balanced. So that means that our driving force is equal to the 3,000 newtons. So because the two forces are equal, that's why it is going at a constant velocity, which was Newton's first law. Now we want to find power. And power is force times velocity. So here's the force. This is the driving force, that is 3,000 newtons times our 30 meters per second. And so we end up with a power of 9 with 4 zeros, 90,000 watts. Remember, watts is the unit for power. And you could also call it 90 kilowatts. So read the question carefully, because sometimes they ask for you to specifically put the answer in kilowatt form. But either way, 90,000 watts or 90 kilowatts. This is our answer for part I. Now let's look at the second part of the question. Okay, the second part of our question says this. The lorry comes to a straight hill inclined at 2 degrees to the horizontal. The driver switches off the engine of the lorry at the point A, which is at the foot of the hill. Point B is further up the hill. The speeds of the lorry at A and B are 30 meters per second and 25 meters per second respectively. The resistance force is still 3,000 newtons. Use an energy method to find the height of B above the level of A. Well, again, we need to draw a good diagram. So here we have our 2-degree incline. Our lorry is going up a hill. We see that it goes from 30 meters per second at point A down to 25 meters per second at point B. We see that the mass is still the same. We see that the resistance is still the same. What's different is the engine was turned off, meaning there is now no driving force. So we've lost the driving force because the engine is off, so nothing is pulling it. And we're going to use an energy method. So one of the things that I would like to mention here is when you have an object on a hill, normally what we have done in the past is we have resolved the mass horizontally or parallel to the inclined plane. When you're working with potential energy, you do not need to resolve the mass parallel to the plane. You might say, how do I remember that? How do I remember when I need to resolve the mass, because driving force is usually going one way and the resistance and the resolve part of gravity is going the other way. How do I know when to resolve it and when not to resolve it? This is what I use to help me remember that. If you're using an energy method where you're using kinetic energy and potential energy is PE. And we also use PE for physical education. So if I am exercising, if I'm doing PE, I don't have to worry about my weight. If I'm not exercising, if I'm not doing PE, then I need to watch my weight. So I use that to help me remember when to resolve the weight and gravity and when not to. Okay, so if you're doing PE, the energy method, you don't need to watch your weight. You don't need to resolve it, the weight with the gravity. If you are not doing PE, if you're not doing the energy method, then you need to resolve parallel to your inclined plane. Okay, so that's what I use to help me. I hope it helps you remember. So since we're going to use the energy method, we do not need to resolve the weight parallel to the plane. So we can go right into our energy formulas. Kinetic energy, again, we're going to see a loss in kinetic energy. So our loss in KE equals 1/2 the mass, 25,000, times the difference, our final velocity squared minus our initial velocity squared. And so our loss in kinetic energy is a very large 3,437,500 joules. And that's our loss in kinetic energy. And now you can see that we have gained potential energy. And our potential energy formula is mass, 25,000, times gravity, 10, times height. Well, we don't know the height. That's what we're solving for. So I'm just going to leave it as h. And so this is going to come out to 250,000 h joules. And so what we want to do is we want to now put this into our total energy. Remember, because we have resistance, we cannot make kinetic energy equal to potential energy because resistance is there. But keep that in mind because you might have a question where there's no resistance and you can just set potential energy equal to kinetic energy and solve for the height. Not in this case because we have resistance. So we use our total energy equation that I gave you before. The work done by the driving force, well, that's 0, minus the work done by the resistance force. Now remember, it's work done by the resistance. This is only force of resistance. Work equals force times distance. So we need to take our 3,000 and we need to find the distance. Well, the distance is this little length of the hypotenuse. So if we take sine of 2 degrees, we get opposite over hypotenuse. And what we need here is the hypotenuse. What is this length? So if we multiply by the d up and divide by the sine 2, our d is equal to h over sine 2 degrees. This is the length over which the 3,000 newtons is being applied. So this is 3,000 times h over sine 2 degrees, and that equals our kinetic energy plus our potential energy. So 2,500, I have to write a little small here, sorry, 250,000 h minus the 3,437,500 437,500 for the kinetic energy. Okay, so the work done by the driving force, well, the engine turned off, no driving force, minus the work done by the resistance. Remember, this is in newtons, we want it in joules, so we got to figure out the hypotenuse there. That's our work done against resistance, equals our potential energy, gain in potential energy, minus the loss in kinetic energy. So notice that this is negative. We can add this to the other side, and we can add this one over here. So if we add the 3,000 divided by sine 2, h, add that over with the 250,000, we get 335,961.125 h equals our, and we add this one to the other side, 3,437,500. Now we have everything in terms of h. Now all we have to do is divide both sides by this value right here, and that's going to give us a height of 10.2 meters to 3 significant figures. Okay, so here is using our energy method and finding kinetic energy, potential energy. Let the positive and negative be determined by gain and loss. And we set that equal to, because we have resistance, our work done by the driving force minus the work done by the resisting force. But make sure you convert it to work or joules, and then you're able to solve the question. Okay, so that's question number 2. Let's look at one more question. Okay, let's read our last question together. Here we have a train of mass 150,000 kilograms ascends a straight slope inclined at alpha degrees to the horizontal with a constant driving force of 16,000 newtons. At a point A on the slope, the speed of the train is 45 meters per second. Point B on the slope is 500 meters beyond A. At B, the speed of the train is 42 meters per second. There is a resistance force acting on the train, and the train does 4 times 10 to the 6th joules of work against this resistance force between A and B. Find the value of alpha. So let's set up our diagram here. Here we have our train on an inclined slope of alpha, which is what our question is asking for. What is this inclined slope? Find alpha. And we have the mass of the train is 150,000 kilograms. We have the speed at A is 45 meters per second, and the speed at B, which is 500 meters down the train track, is 42 meters per second. We have a driving force of 16,000 newtons, and it's a constant force. And we need to find alpha. So again, you're going to have to consider, because it doesn't specifically say use the energy method, you're going to have to look at the information and weigh it out as to which way you want to solve it. You want to solve it using Suvat and Newton's second law, net force, that kind of way, or do you want to use the energy method? Well, of course, even though you sometimes can solve it both ways, for me, the clue is we're looking for, or we have joules. That's a clue right there. Joules is the form that energy is in. So that's a benefit towards the energy way. Also, we don't know alpha. So if we didn't use potential energy, that means we would have to resolve our weight horizontally or parallel to the inclined plane. And that would be difficult to do without this alpha. But that's not saying it couldn't be done. Alpha would at least be your variable that you're solving for. So because we have joules here and because we also have our start and final velocity, I'm going to use the energy method. Plus, this is the video that we're doing energy method for, okay? So we're gonna do it with the energy method, not saying it couldn't be done with Newton's second law and using force, your net force. Probably could. Okay, we're gonna do the energy method. So let's first look at kinetic energy. We have a loss in kinetic energy. Our loss in kinetic energy equals 1/2 our mass, 150,000, times our final velocity squared minus the initial velocity squared. And so we end up with a total of a negative 19,575,000 joules. A lot of energy there because it's a very big train, a lot of weight. So the final velocity squared minus the initial velocity squared. Make sure you square them before you subtract. Don't subtract and then square. Square them before you subtract them. And so here's our loss in kinetic energy. Then if we look at our gain in potential energy, because we're going up, we need to find the height here. And so here's our height. So sine of alpha equals opposite over, and our hypotenuse is 500. So the height equals 500 sine of alpha. So we still end up with an equation in terms of alpha. So PE is mass, 150,000, times gravity, times 10, times 500, our height, sine alpha, which when we calculate our PE, that's 750 million sine alpha. So 100,000 to 750 million sine alpha joules. Now we want to set up our total energy because we have resistance here. So we have to change our driving force into work. Right now it's newtons, we want joules. So for our driving force, work for our driving force is equal to 16,000 force times distance over 500 meters. And so our driving force gives us 8 million joules. And our work and resistance is already in joules. So now we're ready to put our formula together. So our driving work done by the driving force, 8 million, minus the work done against resistance, 4 times 10 to the 6th, equals our gain in potential energy, 750 million sine alpha, minus our 19,575,000 loss in kinetic energy. So here's our alpha here. So if we add this over here to this side, we end up with 700, and if we add this to the other side, we end up with 750 million sine alpha equals 23,575,000. And then when we divide by the 750 million, we get sine alpha, can you see that there, equals 0.03143. And then when we solve for alpha from that, I'll put it over here. put it back here. Alpha then will equal a 1.8 degrees. Okay, so this is just working out all the algebra, but setting it up is important. Your work done by the driving force minus the work done against resistance equals your gain in potential energy minus your loss in kinetic energy, and the loss is why it's negative. And then you just get alpha on one side, the others on the other side. Inverse sign, don't forget to inverse sign, and don't forget to check to make sure your calculator is in degree mode. Inverse sign, and your alpha equals 1.8 degrees. So there we are, 3 examples of using the energy method. It's not too difficult once you get the hang of it. Again, remember when you're using PE, you don't have to watch your weight. You don't have to resolve it parallel to your inclined plane. If there is no resistance, remember that you can set kinetic energy equal to potential energy. That energy is conserved, but there has to be no resistance. Otherwise, you're going to use this energy formula of the work compared to energy. Okay? So I hope that helps, and I hope you have enjoyed our series on mechanics, and you can look for videos that cover entire past papers to help you work through an entire test set all at once. Hope you enjoyed it. Hope to see you again next time.